Okay, let's just dive right into this explainer because today we're going to completely shatter basically everything you thought you knew about artificial intelligence. We hear the term machine learning thrown around literally all the time, right? In the news, at work, on social media. But what is actually happening behind the curtain? Well, we're taking a really structured look at the foundational concepts today, drawing directly from Andrei Burkov's fantastic text, The 100-Page Machine Learning Book. And honestly, the truth of how this all works might just surprise you.
See, right out of the gate, author Andrei Burkov hits us with this incredibly blunt, counterintuitive truth. Machines don't learn. I know, it feels completely backwards given the name. But the reality is, what we casually call a learning machine is actually just a mathematical formula. It's an algorithm. It's just crunching numbers to find patterns in a giant collection of inputs that we call training data. It produces the outputs we want, sure, but not through any kind of actual comprehension. It's all just complex mathematical alignment.
And I think this comparison brilliantly illustrates the difference between actual biological learning and machine learning. Think about playing a video game. If you, a human, learn how to play a game and then someone comes along and rotates your screen slightly, you adapt instantly, right? You still know exactly how to play. But a machine, if you even slightly distort its inputs, like rotating that screen, its output goes completely off the rails. Unless it was explicitly mathematically programmed to recognize that specific rotation, it completely fails. It totally lacks that adaptable comprehension that we see in animal learning.
So you're probably asking, if machines aren't actually learning, why on earth do we call it that? Well, looking back to 1959, Arthur Samuel, an AI pioneer over at IBM, coined the actual term machine learning. Throughout the 1960s, IBM used this cool, futuristic-sounding phrase primarily to attract top talent and impress their clients. It's a lot like how they heavily pushed the term cognitive computing in the 2010s just to stand out in the market. The word learning here, it's just a marketing analogy. It was never meant to be a literal truth.
Okay, moving on to Section 1, 4 Ways Machines Learn. Let's look at the types of algorithms.
So the whole ecosystem really breaks down into 4 main buckets. First up, we have supervised learning. This relies on perfectly labeled data. It's kind of like teaching a system using meticulously organized flashcards. Next is unsupervised learning, where the machine is just handed unlabeled data and essentially told, hey, go find the hidden structures or clusters yourself. Then there's semi-supervised learning, which is a mix of both, usually just because labeled data is super expensive to get. And finally, reinforcement learning, where the machine basically lives in a digital environment, perceiving its state as a vector of features and taking actions specifically to maximize its expected rewards.
All right, Section 2, Deep Dive into Supervised Learning.
Since it's absolutely the most frequently used type of machine learning in practice today, we're going to zoom all the way in on supervised learning. To simplify things, this pipeline breaks down into 4 sequential steps. First, you gather your data. Second, you convert that messy real-world data into numeric feature vectors. Third, you assign numeric labels to those vectors. And fourth, you finally apply your learning algorithm to build a statistical model. It's essentially a systematic process of transforming real-world chaos into structured, machine-readable statistics. Let's actually walk through exactly how this works using a classic everyday example: spam detection. First up, we need to understand the feature vector. If we want to filter spam, you have to remember that a machine can't just read an email like you or I do. A data analyst must first figure out how to translate those human-readable messages into a multidimensional string of numbers. Every single dimension in this vector describes some specific, measurable feature of that email. A really common way to create this vector is what's called the bag of words method. Imagine taking a standard English dictionary of, let's say, 20,000 alphabetically sorted words. The algorithm looks at your incoming email. Does it contain the word A? No, that gets a 0. Does it contain the word Aaron? Yes, that gets a 1. It literally repeats this exact process 20,000 times until the entire textual email is represented as a massive 20,000-dimensional list of 1s and 0s.
Okay, so now the input is machine-readable, but our human labels still aren't. Algorithms like the support vector machine, or SVM, which we're going to use for this example, require us to convert our text labels into cold, hard numbers too. So our spam label simply gets assigned a numeric value of +1, and our not spam label gets a value of -1. Boom! Everything is now purely numeric.
Which brings us to Section 3, drawing the decision boundary. Now that we have all our mathematical inputs, the positive and negative ones, mapped to our giant 20,000-dimensional vectors, let's look at how the algorithm actually draws the line between annoying spam and a totally safe message.
This is where the mathematical magic happens. The SVM algorithm takes all those emails and maps them onto an insanely complex 20,000-dimensional imaginary plot. I mean, just try wrapping your head around a 20,000-dimensional space. In that high-dimensional space, it mathematically attempts to draw a flat surface called a hyperplane straight down the middle, separating all the positive spam examples on one side from the negative safe examples on the other.
The technical term for this separating line is the decision boundary, and the exact shape and placement of this boundary are computed algorithmically based strictly on the training data you provided. This boundary is, well, it's everything. It completely determines the accuracy of the model. When a brand new email arrives, if it mathematically plots on one side of this boundary, boom, flagged as spam. If it plots on the other side, it safely goes right into your inbox.
I absolutely love this quote from statistician George Box that Burkhoff features prominently in his text. All models are wrong, but some are useful. It is just such a vital reminder for anyone working in or looking at this field. That incredibly complex 20,000-dimensional decision boundary we just talked about, it is not a manifestation of perfect, infallible intelligence. It is, ultimately, just statistical estimation based on historical data. It will absolutely make mistakes, but it's incredibly useful.
And finally, Section 4, Predicting the Unknown.
Okay, so you might be wondering, if this entire system is just a mathematical boundary based entirely on old, historical emails, why does this model actually work when it encounters completely new data it has never, ever seen before? Well, it all comes down to a core statistical assumption. Assuming your training examples were selected randomly and independently, the math suggests that a brand new, unseen safe email will likely plot somewhere very close to the old safe emails in that vast dimensional space. It naturally lands near its statistical neighbors, which keeps it safely on the correct side of the decision boundary.
Of course, to minimize the probability of making errors on weird, borderline emails, the machine takes some mathematical precautions. For one, the larger the training set you provide, the more unlikely it is that new examples will lie super far away from the training data. But more importantly, the SVM algorithm explicitly tries to draw that decision boundary so it has the largest possible margin. It actively wants the line to be positioned as far away from both the spam cluster and the safe cluster as mathematically possible. It's essentially building itself the widest possible buffer for future errors.
But this brings us to a fascinating and honestly pretty crucial limitation. Since a machine learning model is essentially just memorizing the statistical distribution of yesterday's data to predict tomorrow, we have to ask the big question, what happens when tomorrow's reality completely breaks the pattern? If the actual nature of spam entirely changes, or the fundamental rules of an environment suddenly shift, that beautifully calculated decision boundary becomes entirely useless. It leaves us to ponder, just how much can we really trust a system that relies entirely on the past to navigate an unpredictable future? Definitely something to think about the next time you hear the words machine learning.